Welcome to the Copper Spice YouTube channel, and thanks for joining us. In this video, we are going to talk about overloading in C++. Overload resolution. Function overloading is not unique to C++, and the basic ideas are simple to explain and understand. The process used by C++ to figure out which overload to call is, however, extremely complex, and many consider this to be one of the more difficult areas of the language. Our talk will present a comprehensive overview of the overload resolution process. We are looking forward to a continued and lively discussion in the comments for this video.
One of the reasons function overloading is both complex and important is because it applies to any function, constructor, or method and most operators. For simplicity, when the term function is used, we are including constructors and methods in this category. There are a few cases where overloading applies specifically to methods, and this will be specifically noted. One of the fundamental principles of overloading is that the order in which overloaded functions are declared is not important. Every overload that is visible to the caller can potentially be called, and making a method private does not hide it from being an overload. There are certain pairs of functions which are not valid overloads of each other. If you write two functions which have the same parameter list and differ only by return type, you will get a compile error. The main reason is since the caller does not have to use the return value, the compiler would never know which return type is the best. It is also not permitted to have two functions with the same parameter list, but different default arguments for those parameters. Changing the value of a default argument does not change the type of a parameter. These two functions will be considered to be identical and not a valid overload. In addition, the static keyword cannot be used as the only difference to overload on, since it would be impossible for the compiler to decide whether to call the static or non-static version of the function.
This example shows the most basic form of function overloading. Here we have two overloads of the function doThing1. The first overload takes one int parameter, and the second overload takes an int and a double. In the first call in main, we are passing the value of 42, which is a single int, so the first overload is invoked. When we pass an int and a double in the second call, the version of doThing1 marked overload 2 will be invoked. These are overloads, however, they differ in the number of parameters, so figuring out which one is called from main is pretty obvious, both to the compiler and to the programmer.
When you have overloaded functions, the compiler needs to have a mechanism for figuring out which function to call. The rules need to be precise and not arbitrary. In the C++ standard, it takes a lot of pages to define this process. If you decide to read clause 16 in the C++ 17 standard, which is where overload resolution is defined, you may also need to consult several other sections of the standard to know the exact rules covering fundamental types, value categories, standard conversions, template argument deduction, s-fine, special member functions, and probably a few more. The process the compiler uses to determine which function to call is referred to as overload resolution. This particular part of the C++ standard is rather daunting to read, even for experienced programmers. As a C++ programmer, it is important to at least understand the basics of overload resolution. At some point, you will need to be able to figure out why a call to an overloaded function is not working the way you anticipated. There are also compiler errors related to overload resolution, and when you understand their meaning, it can make fixing the code a bit easier.
The overload resolution process is performed at compile time. The compiler compares the argument types you have used to call the function with the parameter type specified in all the possible functions which could be called. Ultimately, if the compiler cannot decipher which overload to call, a compiler error is generated with some type of message indicating the call is ambiguous. Template functions are considered during the overload resolution process. Templates act just like normal functions. However, if a template and a non-template function are otherwise equal, the non-template function will be preferred. In the first step of overload resolution, the compiler generates a list of all possible candidates. This list initially includes every function which is potentially callable. If a template function has the correct name, its arguments will be deduced using the normal template argument deduction rules, and the resulting template instantiation will become another candidate in the candidate list. Once the candidate list is generated, the compiler throws out invalid candidates. The standard refers to invalid candidates as not viable. A candidate can be invalid for two different reasons. If the number of arguments passed is not a match for the number of parameters the overload requires, the candidate is invalid. Since parameters with default arguments do not need to be passed, this may not throw out as many overloads as you may think. Even if the argument count is a match, there may be no implicit conversion from a passed argument to its corresponding function parameter. If any of the arguments cannot be converted, the function is also deemed invalid.
The process of deciding which overloads are invalid involves looking at each overload and determining if the passed arguments can be converted to the right data types for this call. At this position in the overload resolution process, the compiler is not looking at which candidate is the best, it is only looking at which ones to toss out. Looking at the call to the function count, we are passing a data type of int and the candidate shown takes a long. The data type of int is implicitly convertible to a long, so this candidate is valid and remains in the candidate list. This candidate may not ultimately be the best match, as there may be a better match for the count function somewhere else in the candidate list. The list of standard conversions shown is a small portion of what's possible. If you're interested in the full list of standard conversions, you may want to look at Clause 7 in the C++ 17 standard. Another source, which may be easier to read, is the section on implicit conversions on CPP reference. The data type conversions we showed in the last slide are called standard conversions, which are conversions between primitive data types built into the language. There are also implicit conversions available between user-defined data types. If you have a constructor which would require an implicit conversion from the passed argument to the received parameter, this is classified as an implicit conversion of a user-defined data type and is kept in the candidate list. User-defined data types are not limited to the classes you write in your application. It's important to mention that many of the classes in the STL and those in the third-party libraries you are linking with may have user-defined conversions, which would satisfy the test for data type convertibility and thus remain in the candidate list.
One of the standard conversion types is called a promotion. The idea of a promotion is to take one data type and extend it to a related data type, which is essentially larger. Integral promotion in C++ is to an int or an unsigned int. It may not be obvious or intuitive, but the C++ standard defines that an int to a long is not a promotion, but rather a conversion. This is very important since a promotion is considered a better match for overload resolution than a conversion. The other type of promotion is floating point promotion, which promotes a float to a double. At first glance, this code looks like it should be fine. We originally thought overload 2 would be a match for the call to do thing 2 passing the value of 42. We assumed an int could be promoted to a long, and this would be better than converting an int to a char. Our understanding of what can be promoted turned out to be incorrect. This code actually results in a compile error, since neither overload 1 nor overload 2 is selected by the overload resolution process. Both overloaded functions require an implicit conversion, which makes them equal in the amount of work, and thus the compiler cannot decide which one to call. So once the compiler creates the candidate list, how does it select the best overload to call? After removing the invalid overloads, the remaining candidates are ranked to find the least bad match. If there is one match which is better than all others, it will be selected and it wins. Otherwise, the process continues or an error is reported.
The idea of this part of the overload resolution process is to sort the remaining candidates based on how much work they require. Ideally, an exact match is desired, and unless there are two exact matches, that candidate will win. A candidate which requires a promotion of the argument data type is a better match than one which requires a conversion. The consideration is what kind of steps and how many are required to transform the passed argument into a data type which matches the receiving parameter. When the compiler puts the candidates in order, it is common for multiple overloads to be equal to each other. If there is no single best match, the compiler can apply a long list of tie-breaking rules to select which one is called. For example, if a template and a non-template function are tied for first place, the non-template is selected. If the compiler applies every tie-breaking rule and there is still no winner, the call is considered ambiguous and the compiler reports an error. The exact error message you may see depends on your compiler, but usually the error will start by indicating an ambiguous function call on a particular line. This message will be followed by a list of the candidates which were considered. Some compilers will list every overload, while others will only list the valid overloads that were considered. In order to solve an ambiguous overload error, there are several things you can change. You should start by looking at the set of overloaded functions the compiler reports to see if you want to add or remove an overload. Often the ambiguous call can be caused by multiple user-defined conversions being available. In this case, it is a good idea to see if some of your constructors should be marked explicit. This will prevent that constructor from being called implicitly to convert an argument. If the ambiguous overloads include templates, make sure your templates are as specific as possible. This may involve using a default value or sFine to prevent certain template functions from being valid candidates.
Another way to resolve ambiguous calls is to use an explicit conversion. Explicit conversions are a way for a programmer to convert the argument before the overload resolution occurs. This will reduce the number of viable candidates and alter what is considered a good match, thus ensuring the desired function is called.
One of the reasons overload resolution is so complex to work with is that current compilers do not provide feedback explaining why they chose a particular overload. As the programmer, you only see the output of the overload resolution process, not the intermediate steps. It would be very helpful if compilers supported a verbose overload resolution mode where you could see how the rules and tiebreakers were applied. In some cases, you can get a small amount of information if the wrong overload is selected by intentionally adding an ambiguous overload to the candidate list and reading the resulting error messages. Most programmers tend to think that template argument deduction is magical and complicated. It is involved, but most of the time the results are not too surprising. It turns out overload resolution is actually far more complex and complicated. One of the complications is that the first step in overload resolution may involve deducing template arguments for various template functions to determine if they should be part of the candidate list. If one of the candidates is a template function with a const reference function parameter, the T will be deduced to the most appropriate data type and this template function will win nearly every overload resolution. This means you should be very careful with template functions that take a const t reference parameter. They may end up matching far more often than you intended.
The purpose of this example is to show why it is important to understand the phases of overload resolution. A const character star is referred to as a C string, which is not the same as a string literal. A string literal, or a quoted string, is an array of characters. Our CS string library has a constructor to convert a C string to a CS string. This constructor is a templated method of a template class. There's an enable if in the declaration of this constructor to ensure the T can only be a const character star or a character star. Since template argument deduction happens before overload resolution, this template constructor will be placed in the list of candidates. Since in this example, we are passing a const character star, this constructor is chosen as the best match during overload resolution. The compiler then instantiates this template constructor. We added a #define to inject a static assert into this constructor. The purpose of the static assert is to cause a compiler error and disallow a C string from being passed. Ideally, it is safer to avoid converting a character star to a CS string, since the encoding of a character star is unknown. In real practice, using the #define to trigger the static assert may not be practical due to legacy code or application usage of C strings. As a side effect, we had to add a type trait test in the static assert to ensure the compiler does not evaluate the static assert until the template is fully instantiated. This mechanism works because template instantiation occurs after overload resolution has selected the best match, even though template argument deduction happens before the overloads are resolved. This is our final example showing overload resolution with multiple parameters. Take a moment to examine the overloaded functions and the function calls and see if you can figure out how these calls will be resolved.
Starting with main in part A, the call to do thing A is considered ambiguous given overload 1 and overload 2. The reason is a bit tricky. Overload resolution considers each argument separately before combining the results. All of the past arguments are int. Overload 2 is a better match than overload 1 for the first argument. For the second and third argument, overload 1 is a better match. This is a case where the idea of a best match differs from what may be obvious. Intuitively, we might say that overload 1 should be chosen because there are more arguments which are an exact match. This is not how the overload resolution process works. What the compiler really does is look at each parameter in isolation. Once the overload process observes that overload 2 wins once, and then overload 1 wins once, the process basically ends and declares this as an ambiguous call.
In the function call to do thing B, there is a winner, and it is overload 3. Again, we are passing 3 int data types. For the first argument, overload 3 is equal to overload 4, since they both declare an int. For the second argument, overload 3 is a better match, as overload 4 would require a conversion. For the third argument, neither overload is a better match, which makes them equal in the number of steps required for implicit conversion. Overload 3 wins because for every parameter, it is either a better match or an equal number of steps to overload 4.
For more information about the CopperSpice libraries and the other open source projects we maintain, please visit our website at www.copperspice.com.
Thanks for watching. We hope you found the content of value. We are looking forward to your questions and feedback, so feel free to leave a comment on this video.
Please make sure you subscribe to our YouTube channel and come back in 2 weeks for our next video.